Fine, let's start. Number 10. Reality is digital, not analog. Here's something nobody tells you when you're a kid learning about the world. For most of human history, we assumed reality was smooth. That if you took anything, a beam of light, a stretch of energy, the warmth coming off a fire, and you cut it in half, and then cut that half in half, you could keep going forever. Smaller and smaller. No bottom. No end. The world was a continuous, flowing thing, like pouring water from a jug. That was the picture. That was common sense. And then, right at the turn of the 20th century, a careful, conservative German physicist named Max Planck ran into a problem he could not solve. He was studying the light glowing off hot objects, and every equation he tried gave nonsense answers. Infinities where there should have been numbers. So, almost in desperation, he tried something he didn't even believe at first. He assumed that energy didn't flow smoothly. He assumed it came in tiny, fixed, indivisible chunks, little packets, and suddenly the math worked perfectly. He called those packets quanta, and that single reluctant guess cracked the universe open. Because it turns out this isn't just true for light. It's true everywhere you look closely enough. Electric charge comes in fixed units. You can have 1 unit or 2 units, but never 1.5. Electrons inside an atom can't sit at just any energy. They occupy specific, discrete levels. And to jump between them, they have to leap, instantly, without ever existing in the space between. There is no in-between. Spin comes in fixed steps. Light arrives as individual photons, one at a time, like coins dropping into a jar. Now sit with that for a second. The universe, at its most fundamental level, does not deal in smooth gradients. It deals in steps, in discrete values, in ons and offs and exact integer amounts. And if that sounds familiar, it should, because that is exactly how a digital system stores information. Your screen looks like it's showing you smooth curves and soft gradients, but zoom in far enough and it's all pixels. Individual squares, each holding one fixed value. Your music sounds like a continuous wave, but it's actually thousands of separate samples per second. Snapshots stitched so close together, your ear can't hear the seams. We built our entire digital world on the idea that you can represent reality with discrete chunks instead of smooth flows. And then we looked at reality itself, as closely as we possibly could, and found out it was already doing the same thing. Now, I want to be honest with you, because that's the whole point of this channel. A physicist will tell you, correctly, that digital is a loaded word here. Plenty of things in physics still look perfectly smooth. Position, for one. And the quantization of energy doesn't by itself prove anybody's running anything. This is a sign, not a verdict. We're at number 10. We're just getting started. But it's a strange place to start, isn't it? We grew up assuming the world was a painting, all blended and continuous. We grew up wrong. The world is closer to a mosaic. And once you notice the tiles, you can't stop wondering who laid them. Number 9. The cosmic speed limit as a bandwidth cap. There is a wall built into the universe, and nothing has ever gotten past it. Not a spaceship, not a particle, not a radio signal, not a gravitational ripple, not a single bit of information. The wall sits at exactly 299,792,458 meters per second. The speed of light. And the universe enforces it with absolute, unbreakable consistency. We usually call it the speed of light, which is a little misleading because it makes you think it's about light. It isn't really. Light travels at that speed because light is massless, so it has no choice. It always moves at the maximum. The deeper truth is that this number is the speed of causality. It's the fastest that any cause can produce any effect, anywhere, ever. It's the speed at which the universe is allowed to update itself. And here's where it gets interesting if you've ever built anything on a computer. Every large system that processes information has a limit on how fast that information can move between its parts. Engineers call it bandwidth or latency, the unavoidable delay built into moving data from one place to another. You cannot run a massive networked simulation without it. If different parts of your world could update each other infinitely fast, the whole thing would fall apart. Calculations would race ahead of each other. Cause and effect would tangle. The system would tear itself to pieces. So what do you do if you're building something enormous and you need it to stay stable and consistent? You impose a maximum update speed, a hard, universal cap that nothing is allowed to exceed, so that every part of the system stays synchronized with every other part. You build in a speed limit, exactly like the one our universe has, and the consequences of our speed limit are genuinely bizarre when you stop taking them for granted. Time slows down for things that move fast. Distances shrink. Two people can disagree about whether two events happened at the same time, and both of them can be right. Reality bends itself into knots to make sure that nothing, ever, outruns that one fixed number. The universe will distort space and time themselves before it lets you break the cap. That's not the behavior of a casual rule. That's the behavior of a hard constraint the system absolutely cannot allow you to violate. Now, again, the honest version. A physicist will tell you the speed limit drops straight out of the geometry of space-time in Einstein's relativity. You don't need a programmer to explain it. The bandwidth framing is a way of seeing it, not a measurement of it. But it's a hard thing to unsee. We spent a century learning that the universe would rather warp time itself than let two things communicate too quickly. And anyone who's ever tried to keep a giant system from outrunning itself knows that feeling exactly. Sometimes the universe doesn't feel like a place. It feels like a process, straining to keep itself in sync. Number 8. The Planck length, the pixel of space-time. We just talked about how fast the universe is allowed to update. Now, let's talk about how small it's allowed to get. Because there's a floor. And the floor is so far down, it makes an atom look like a galaxy. It's called the Planck length. Written out, it's about 1.6 times 10 to the minus 35 meters. I could say that number out loud all day, and it wouldn't mean anything. So let me try to make it real. If you took a single atom and blew it up to the size of the entire observable universe, the whole thing, every galaxy, billions of light years across, then, on that absurd, inflated scale, the Planck length would be about the size of an average tree. That's how far below the atom this is. It is the basement beneath the basement, beneath the basement. And here's what makes it special. The Planck length is not just really small. It's the scale at which the very idea of distance stops working. Ask a physicist how far apart 2 points are when they're closer together than the Planck length, and the honest answer is that the question stops having meaning. Our best theories, quantum mechanics on one side, gravity on the other, both break down completely. Below this scale, smooth space appears to simply stop. There is no finer detail to describe. There is no smaller. Does that ring a bell? Because that is the precise definition of a pixel. A pixel is the smallest unit of detail on a screen. You cannot zoom in past it. Ask what color the screen is at a point smaller than 1 pixel, and the question is meaningless. There's nothing there to answer it. The image has a resolution, a bottom limit of detail, and below that limit the concept of where exactly just dissolves. The universe seems to have a resolution too, and here's the part that genuinely gives me chills. This number, the Planck length, isn't something we measured by building a smaller and smaller ruler. We could never build a ruler that small. We calculated it by taking three of the most fundamental constants in all of physics: the strength of gravity, the quantum constant that Max Planck discovered, and the speed of light, and combining them. Three completely separate rulebooks. Gravity, which governs galaxies, quantum mechanics, which governs particles, and the cosmic speed limit. Three rulebooks that have nothing obvious to do with each other. And when you combine them, they all point to the same smallest tick, the same bottom of reality. It's as if you opened three unrelated instruction manuals, written by three different authors, and found that all three agreed exactly on the size of the smallest possible thing. The skeptic's view, and it's a fair one, the Planck length might just be where our current physics runs out of road. The place where we need new theories, not necessarily proof of literal pixels. And remember, we're going to meet a machine in a few minutes that actually went looking for those pixels, with a real result you might not expect. But the floor is there. Reality has a bottom. And every time I think about it, I picture someone zooming in on an image, closer and closer, waiting for it to keep getting sharper, and instead hitting the point where it simply can't. Number 7, the cosmic ray ceiling. Everything so far has been a way of seeing things, a reframing. Now, I want to show you something different, because this one is a real, published, peer-reviewed scientific paper that proposed an actual test for whether we live in a simulation, not philosophy, an experiment. Start with cosmic rays. Out there in space, nature builds particle accelerators that make anything we've constructed on Earth look like a toy. Exploding stars, monstrous black holes, things we don't fully understand. They fling individual particles across the cosmos at almost unimaginable energies. We detect them when they slam into our atmosphere. And for decades, physicists noticed something odd. The most energetic cosmic rays seem to hit a ceiling. They cut off sharply, right around an energy called the GZK limit, named after the three scientists who predicted it: Greisen, Zatsepin, and Kuzmin. Now, there's a perfectly ordinary explanation for that ceiling. The idea is that the very highest energy particles lose their energy by bumping into the faint afterglow of the Big Bang as they travel, so they can't reach us with more than a certain punch. Standard physics. Nothing spooky. But in 2012, three physicists, Silas Bean, Zora Davuti, and Martin Savage, looked at that ceiling and asked a wild question. They study something called lattice simulations. When physicists today want to simulate a tiny piece of the universe on a supercomputer, they can't use smooth, continuous space. It's too much to compute. So they lay down a grid, a lattice. They calculate what happens only at the grid points, like pinning the universe to a piece of graph paper. It's the standard trick for simulating physics. And here's what they realized. If you simulate the universe on a grid like that, the grid leaves fingerprints. For one thing, a grid imposes a maximum possible energy. A particle simply can't carry more energy than the grid spacing allows. A built-in ceiling. And they did the math. And the kind of ceiling a cosmic grid would create looked uncomfortably similar to the cosmic ray cutoff we actually see. But they went further, and this is the part that gets me. They pointed out that a grid isn't perfectly smooth in every direction. A grid has axes, edges, preferred directions, the way a sheet of graph paper has lines running up and down and left and right, but not diagonally. So if our universe were running on a cosmic lattice, the highest energy particles should travel slightly more easily along the grid's axis than across them. They should show a subtle directional bias, a faint preference for certain directions in the sky, secretly tracing out the structure of the simulation we're living inside. And that is a thing you can actually look for. You can study the directions the highest energy cosmic rays come from and ask whether there's a hidden pattern, a grain in the wood of reality. To be clear, they have not found it. No grid axis bias has turned up in the data, and the ordinary explanation for the cosmic ray ceiling works fine without any simulation at all. The authors themselves were upfront that this assumes whoever's simulating us uses the same tricks we do, just scaled up unimaginably. It's a thought experiment with teeth, but think about what just happened. Serious physicists in a serious journal said, if we are inside a simulation, here is the smudge it would leave on the sky. Here is how you'd catch it. For one quiet moment, the question stopped being a late-night thought and became an experiment. And the sky is still up there, waiting to be read. Number 6. The universe only renders when you look. If you've ever played an open-world video game, you know a secret about how it works, even if you've never thought about it directly. The game is not rendering the entire world all the time. It can't. It would melt the machine. So it cheats. It only draws, in full detail, the part of the world you're actually looking at. Turn the camera away, and the scene behind you quietly stops being computed. The mountains aren't really there until you look at them. The engine renders on demand. Now, I'm going to tell you about the single strangest fact in all of physics. And I want you to keep that game in the back of your mind. It's called the double slit experiment, and it has been driving physicists quietly insane for 100 years. You fire tiny particles, electrons, photons, doesn't matter, one at a time, at a barrier with 2 narrow slits in it, and you let them land on a screen behind. Now, common sense says each particle goes through one slit or the other, like a tiny marble. You'd expect 2 simple stripes on the screen. That is not what happens. Instead, you get a striped pattern of many bands. The unmistakable signature of a wave passing through both slits at once and interfering with itself. A single particle, fired alone, somehow goes through both openings at the same time and ripples like a wave. One particle, both paths, at once. So, naturally, physicists wanted to catch it in the act. They put a little detector at the slits, just to see which one each particle really goes through. And the moment they do that, the moment they look, the particle stops behaving like a wave. It picks one slit, like a normal marble, and the striped pattern vanishes. The 2 simple stripes come back. Read that again. When nobody checks which path it took, the particle takes all paths as a smear of possibility. The instant someone checks, it collapses into one definite answer. The act of observation is what forces reality to commit, and it gets worse, or better, depending on your mood. In 2022, 3 physicists won the Nobel Prize for experiments confirming something even deeper. It's not that the particles secretly had a definite path all along, and we just didn't know it. The experiments show the definite answer genuinely does not exist before the measurement. The universe isn't hiding the value from us. The value hasn't been computed yet. So here's the picture, laid bare. Until something observes it, a quantum system exists as a cloud of unrealized possibilities. Only when it's measured does it snap into one concrete state. The universe does not seem to bother nailing down the fine details until someone is looking. It renders on demand. Now the honest part, because this one gets wildly overstated online. Observation here does not require a conscious mind. It doesn't need a human, or a soul, or magic. It means a physical interaction with the system. And there are interpretations of quantum mechanics, like the many worlds idea, that explain all of this without any collapse at all. The video game parallel is a metaphor, not a proof. I'm not going to lie to you and pretend the case is closed. But strip away the arguments, and you're left with the bare experimental fact. And the fact is genuinely unsettling. Reality, at its foundations, keeps its options open until it's forced to choose. It computes the answer at the last possible moment, only when the answer is needed. And if you've ever watched a game quietly refuse to draw the world behind your back, you already know that trick. You've just never had to wonder if you were standing inside it. Number 5. The error correcting code. Hidden in the equations. Okay, this is the one. If there's a single fact in this entire video that made me sit up straight the first time I heard it, it's this one. And it comes not from a mystic or a YouTuber, but from one of the most respected theoretical physicists in the world. His name is James Gates. He spent his career on something called supersymmetry, a deep, elegant idea about the most fundamental particles and forces in nature, the kind of math that lives at the very bottom of string theory and the search for a final theory of everything. This is hardcore physics, equations most people will never see, describing the deepest structure we know how to describe. While he was working through these equations, Gates and his collaborators kept running into certain mathematical structures, and they gave them a name, adinkras, borrowed from symbols used in West Africa. Think of them as diagrams that capture how the pieces of these supersymmetric equations connect to one another. Just a tool for keeping track of very abstract relationships. And then they looked closer at the adinkras, and they found something inside them that should not have been there. They found error-correcting codes. Now, I need you to understand what an error-correcting code actually is, because the words sound dull, and the reality is anything but. When your computer sends information across the internet, off a scratched disk, through a noisy signal, some of it inevitably gets corrupted. Bits flip. Noise creeps in. So engineers invented a brilliant fix. They build extra structure into the data, cleverly arranged, so that when an error sneaks in, the system can automatically detect it and repair it. The message heals itself. Error-correcting codes are the reason a scratched DVD still plays, the reason a weak signal still gets through clean. They are a deliberately engineered safeguard. They exist for exactly one purpose: to protect information from corruption. We invented them. They are one of the most distinctly human, distinctly digital things we have ever made. And James Gates found them sitting inside the equations that describe the fundamental fabric of reality. Specifically, a particular class of them, doubly, even self-dual linear binary error correcting block codes. The same family of codes that, in slightly different form, run inside the browser you might be watching this on right now. Gates himself has said he was stunned. He's spoken openly about the question it forces. He said, more or less, that finding computer code, the kind that makes browsers work, buried deep in the equations we use to describe the universe, it raises the possibility that we are living in something like the Matrix. A serious physicist saying that in public. Now let me give you the cold water, because Gates gives it himself, and that's part of why I trust him. He's careful. He doesn't claim this proves anything. It's possible these codes are an artifact of the particular way these equations are organized, a reflection of the math we chose, not a message from a programmer. Many physicists see it as a beautiful, genuine puzzle that we don't yet fully understand, and they leave it at that. But step back and feel the shape of it. Of all the things you might expect to find at the bottom of physics: symmetry, beauty, simplicity, sure. But error-correcting code? A safeguard whose only reason to exist is to keep information from degrading? That's not something you stumble into by accident in nature. That's something you find inside well-written software. Gates went looking for the rules of reality. And tucked into the deepest equations we have, he found something that looked, unmistakably, like it had been engineered to keep the program from crashing. Number 4. The machine built to hunt for the pixels. A few minutes ago, I told you about the Planck length, the idea that reality might have a smallest possible size, a resolution, like the pixels on a screen. And I said it was something we calculated, not something we measured, because no ruler could ever be that small. Well, some people don't like leaving things at we could never measure that. So they tried. At Fermilab, the Great Particle Physics Laboratory in Illinois, a physicist named Craig Hogan had a daring idea. If space-time really is grainy at the smallest scale, if it's pixelated, encoded at some fundamental resolution rather than perfectly smooth, then that graininess should produce a tiny, restless jitter, a faint trembling in the fabric of space itself. He called it holographic noise, and he reasoned that if you built a sensitive enough instrument, you might actually be able to feel that tremble. You might be able to detect the pixels of reality shivering. So he built the machine. It's called the holometer, and it is a beautiful, slightly mad piece of engineering. Picture two long arms, each about 40 meters, stretched out at right angles to each other. Down each arm, you fire a powerful laser. The light bounces off mirrors and comes back, and you overlap the two beams with exquisite precision, so precise that you can detect a wobble in space far, far smaller than a single proton. If spacetime were jittering the way Hogan's theory predicted, the holometer would see it. It was, at the time, one of the most sensitive instruments of its kind ever built, designed for the sole purpose of asking the universe, directly, whether it's pixelated. Let that sink in for a moment. Separate from whatever the answer is. Human beings looked at the wildest question you could possibly ask. Is reality grainy? Is it encoded? Are we made of something like pixels? And instead of arguing about it over drinks, they built a machine to go and check. We constructed a physical detector to test whether we live in something resembling a simulation. That, by itself, is one of the most astonishing things our species has ever done. So what did it find? In December of 2015, after a year of collecting data, the result came in, and the holometer did not detect Hogan's holographic noise. To a high degree of confidence, it ruled out his specific model of a pixelated universe. The jitter he predicted, at the scale he predicted it, was not there. Now, I could hide that from you and keep the spooky vibe going. But that's not what this channel is. The honest result is a null result. Spacetime, at the level the holometer could probe, did not show the graininess that one particular theory expected. A lot of physicists, frankly, weren't surprised. But here's why it still belongs on this list, and why I find it strangely hopeful. Hogan himself said it best. This is just the beginning of the story. A null result doesn't kill the question. It kills one version of it and sharpens the next. We didn't disprove that reality has a resolution. We proved that if it does, it doesn't shimmer in the exact way we first guessed. The Planck length is still down there. The floor of reality is still real. And we now have a new way of interrogating space and time that we simply did not have before. The machine worked perfectly. It asked the universe a clear question and got a clear answer. The answer just happened to be, not like that, keep looking. Which, if you think about it, is exactly what the universe always says, right before it shows you something stranger. Number 3, the universe runs on information. We're getting close to the top now, and the ideas are getting bolder. So let me introduce you to a physicist who is saying, out loud and in print, the thing most scientists only whisper. His name is Melvin Vopson, and he works at the University of Portsmouth in England. And for years now, he has been building a case around a single radical idea: that information is not an abstract concept we invented to describe the world. Information is physical, a real, fundamental ingredient of reality, sitting right alongside matter and energy. He's gone so far as to propose what he calls a mass-energy information equivalence principle. You know Einstein's famous equation, the one that says mass and energy are two forms of the same thing. Vopson's claim is that information belongs in that family too, that a bit of information has a tiny, real, physical mass. He's even suggested that information might be a fifth state of matter, after solids, liquids, gases, and plasma. If he's right, then every time you store or erase data, you are, in a literal physical sense, changing the amount of stuff in the universe. But the part that lands us on this list is something he calls the second law of infodynamics. Now, you've probably heard of the ordinary second law of thermodynamics, the famous rule that says disorder, entropy, always increases. Things fall apart. Order decays. Your coffee goes cold. Your room gets messier. The universe slowly winds down. That's the most reliable trend we know. Vopson studied the entropy of information specifically, the disorder inside information systems, and he claims it does the opposite. He argues that the information entropy of a system stays the same or actually decreases over time. Things get more ordered, more compressed, more efficient. And think about where you've seen that behavior before. A system that automatically reorganizes its information to be as compact and orderly as possible. That's not how nature usually behaves. That's how software behaves. That's a program compressing files, cleaning up memory, optimizing its own storage so it doesn't waste space. If you were running a simulation the size of a universe, minimizing the information you had to track would be exactly the kind of efficiency you'd build in. Vopson has looked at this across digital data, across genetics, across the physics of atoms, across cosmology. And he argues the same tendency keeps showing up. And he doesn't dance around the implication. He has said, plainly, that his findings provide scientific evidence that appears to underpin the simulated universe hypothesis. He even more recently argued that gravity itself might be a kind of computational effect. The universe organizing matter to keep its information tidy. Here's my obligation to you. This is contested, genuinely contested. The mass energy information equivalence has not been confirmed in a lab. A lot of physicists do not accept that the second law of infodynamics is a real law of nature at all, and they regard the simulation framing as a leap well beyond the evidence. This is not settled science. This is a credentialed scientist out on a limb, and the limb might not hold. But I keep coming back to one thing. We're so used to thinking of the universe as made of stuff. Particles, fields, energy. And here's a physicist saying, no, look closer. The stuff might be secondary. The thing underneath might be information. Bits. And a universe that is fundamentally made of information, constantly compressing itself to run more efficiently, is not a universe. It's a computation. And computations are run by something. Number 2, the universe has a maximum compute budget. If the last idea felt like it was on the fringe, this one is the opposite. This comes from a brilliant, completely mainstream physicist at one of the best universities on Earth, and it's some of the most rigorous work in this entire video. And honestly, it might be the most quietly mind-bending thing on the list. His name is Seth Lloyd, and he works at MIT, and he is one of the founding figures of quantum computing, the field that's trying to build computers out of the strange rules of the quantum world. And at some point, Lloyd asked himself a question so audacious it sounds like a joke. If the universe is processing information, and at the quantum level, every particle interaction really does behave like a tiny computation, then how much computing has the entire universe done since the Big Bang? What's the total? Can you actually put a number on it? And the staggering thing is, he could. In a paper titled, simply, Computational Capacity of the Universe. Lloyd worked it out. He treated the cosmos as one enormous quantum computer, with every elementary particle acting as a kind of bit, and every interaction between particles acting as a logical operation, the universe computing its own next moment, over and over, since the beginning of time. And he found the limit. Since the Big Bang, the universe could have performed, at most, around 10 to the power of 120 operations. That's a 1 followed by 120 zeros. and it could have done this on, at most, around 10 to the power of 90 bits of information, or 10 to the 120 if you fold in gravity itself. These are finite numbers. Enormous, beyond comprehension, but finite. The universe has a maximum amount of computing it has ever been able to do. It has a ceiling. Now here is the detail that genuinely raised the hair on my arms. Those numbers, the total operations, the total bits, aren't arbitrary. Lloyd showed they fall right out of a handful of the universe's most fundamental constants. Planck's constant, the quantum number again, the speed of light, our cosmic speed limit, the strength of gravity, and the current age of the universe. Plug in those few basic facts about reality, and out pops the spec sheet. The total memory, the total processing power, the complete computational budget of existence. A spec sheet, like the one on the side of a computer box. Memory, processing speed, capacity, for the universe. I want to be fair, because Lloyd himself is careful about what this means. He is not claiming we're living in someone's simulation. His point is subtler, and in a way, even stranger, that the universe doesn't just resemble a computer, it physically is one. It is literally processing information through every interaction, all the time. Whether that computer is the bottom level of reality, or whether it's itself a program running on some deeper machine, that Lloyd doesn't claim to know. He just hands you the numbers. But sit with what those numbers mean. We can calculate the universe's total memory. We can calculate how many operations it's allowed to perform. We can measure its bandwidth. We found its pixel size. We caught it rendering on demand. And we found error-correcting code in its source. Every single thing you would need to describe a computer, we have now, one way or another, found in reality. And there's exactly one thing left to ask. If the universe is a computation with a finite budget and a fixed set of rules, then what wrote the rules? Which brings us, finally, to number one. Number one, the unreasonable effectiveness of mathematics. Everything we've talked about so far has been a clue. A property of reality that looks suspiciously digital, suspiciously engineered, suspiciously computed. But underneath every single one of them is one deeper mystery. And it's so basic, so woven into everything, that most people go their whole lives without ever noticing it's strange. The universe obeys mathematics, and it has no obligation to. In 1960, a physicist named Eugene Wigner, a Nobel Prize winner, one of the sharpest minds of the 20th century, wrote a short essay with a haunting title. He called it The Unreasonable Effectiveness of Mathematics in the Natural Sciences. And in it, he pointed at something that had quietly bothered him his whole life. Why does math work so well? Not just okay, absurdly, impossibly well. Think about what mathematics actually is. It's patterns in the human mind. Symbols on paper, rules we invent and play with, often for no reason at all, except that they're beautiful or interesting. And yet, over and over again, those abstract scribbles turn out to describe the physical universe with a precision that defies all reason. Let me give you the example that still stuns physicists. Using the math of quantum theory, you can predict a certain magnetic property of the electron. And when you compare that prediction to what we measure in the lab, the two agree. Not to 2 decimal places, not to 5, to around 12 decimal places. 12. That's like predicting the distance from New York to Los Angeles and getting it right down to the width of a single human hair. From symbols on a page. The universe has no reason to be that obedient to our equations, but it is. And it gets stranger. Again and again, mathematicians have invented entire fields of pure math with absolutely no application in mind, just exploring abstract structures for their own sake. sometimes proudly insisting their work was useless. And then, decades or centuries later, a physicist reaches for exactly that math and discovers the universe was built on it all along. The geometry needed for Einstein's curved spacetime was worked out by mathematicians half a century before Einstein needed it for no physical reason at all. The strange math of imaginary numbers, invented as an abstract curiosity, turned out to be the native language of quantum mechanics. It's as if the answer key was written before anyone asked the question, as if the source code was sitting there, waiting, and we kept stumbling onto pieces of it. Wagner's own words were that this is a wonderful gift which we neither understand nor deserve. He called it a miracle, and he meant it almost literally. A thing for which we have no explanation. Now, the skeptics have answers, and they're worth hearing. Maybe we evolved as pattern finders, so of course we describe reality in patterns. Maybe we only remember the math that worked and quietly forget the rest. Maybe the universe obeys math is a little circular because we built physics out of math in the first place. Those are real responses, and I don't dismiss them, but none of them quite reach the bottom of it. None of them quite explain why reality is compressible at all, why a cosmos this vast and complex can be captured in a handful of short, elegant equations small enough to print on a t-shirt, why there are laws, why the universe is the kind of thing that can be calculated. And that's where this whole journey lands. Because there is one kind of system we know of that runs on mathematics, that obeys precise rules, that can be described completely by code, that has a resolution and a speed limit, and a finite memory and error correction woven through it. A program. Software. Something that was written. We started at number 10 with a quiet little fact. That reality comes in discrete chunks instead of smooth flows. And step by step, the universe kept handing us the same kind of clue, over and over, until we arrived here, at the oldest and deepest question of all. Not, what is the universe made of? But, why is it the kind of thing that follows rules? Why is there math underneath everything? And where did it come from? We don't know. We may never know. Maybe it's a brute fact, the way things simply are. Or maybe, the reason the universe reads like it was written in mathematics is that somewhere, somehow, someone wrote it first. And we are the ones living inside the sentence, looking up, slowly learning to read. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.